thank you very much for that introduction, Mark and Jenny, and thank you very much to you all for hanging around for this last talk of the day. So yeah, I'm just going to pick up a little bit from where Mark has left off there, and I suppose we've started to do some work in the last sort of 10 years, I suppose now, looking at some of the impacts on substrate metabolism, picking up some of the work that Mark's done there, and also some potential effects on glucose homeostasis that we're seeing with the berries as well. Just thought I'd make it clear from the start. So the research that I'm going to present here that I've and the team at Liverpool John Moores have done, that was in a previous employment, and it was last July that I actually moved to work for Precision Fuel and Hydration in the UK, so slightly different tact. I'm in industry now, but still involved in some of the research that's ongoing at Liverpool John Moores University at the moment. So Mark's done a fantastic job of giving you a bit of an introduction to anthocyanins and some of the biochemical aspects of those berries that Jenny talked about. I can probably give you a little bit of background to my introduction to anthocyanins, and it was probably around 2015 that I received a very enthusiastic email from Mark Willems. I can't remember the exact message, but it was something along those lines. And Mark was very enthusiastic about the potential for anthocyanin and blackcurrant anthocyanins in research and some of the effects that he's talked about today. Now, I'll be honest, I did read that email with a healthy dose of skepticism, and I wasn't quite sure what this guy from the south of England at the time, what he was really as excited about. But anyway, you go to PubMed and you start to do your due diligence. And one of the first papers I came across was one of the papers from Mark's lab. This was looking at blackcurrant extract and some of the improvements in cycling performance that he's already told you about. But I was, I suppose, intrigued by the potential or the result that's in this title here, showing that there's a potential improvement in fat oxidation. And that kind of fit quite nicely with the research that I was doing at the time, and I suppose my research themes, because I've always been interested in how we can use nutrition and or exercise training to manipulate substrate metabolism, and then what impact is that going to have on performance, but then also potentially metabolic health, and then also some of the underlying mechanisms for that. And so just to cover this study off that Mark talked about here, so this was 300 milligrams of blackcurrant extract, about 105 milligrams of anthocyanins for 7 days, and on the 7th day those participants, these were just recreationally active healthy individuals, arrived at the lab, undertook an exercise test at these different exercise intensities, and what they saw here was that there was this significant increase in fat oxidation following the blackcurrant extract supplementation at 65% of VO2 max. So I was intrigued by this, and Mark followed up his email with some interesting data at the time that he hadn't quite published and has now obviously published a couple of years later. That was showing us or interested in looking at the dose response effects of these blackcurrant extract on substrate oxidation. And this was during prolonged cycling. So again, this was a 7-day supplementation with either a placebo, 300, 600 or 900 milligrams of blackcurrant extract per day. Again, this was recreationally active male individuals. And I've just presented here, we've got the RER data and the fat oxidation data. So we can see it was a natural decrease in RER and an increase in fat oxidation during this 2 hours of cycling at 65% of VO2 max. And when we look at the mean rate of fat oxidation during that exercise period, there was a small but non-significant increase with 300 milligrams per day. But when we moved to 600 and 900 milligrams per day, we saw that, or Mark saw that there was this sort of 20 to 24% increase in the rate of fat oxidation. So aligns with kind of what he talked about in his talk about the sort of magnitude of change that we're able to observe using this supplement. So again, intrigued here. So one of the reasons that Mark actually contacted me, I suppose, and Liverpool John Moores, was because he was struggling to find female participants interested in taking blackcurrants in the south of England. And thankfully I knew quite a few females in the north of England who were relatively endurance trained. I should probably not put it like that. We had a decent pool of fairly well-trained female athletes who would be keen to take part in research, for sure. And so we set about answering this question as to whether this short-term blackcurrant extract supplementation could increase whole body rates of fat oxidation in females during prolonged cycling. And again, used a similar protocol to that of Mark. We actually recruited 16 trained females, so VO2 max 44 mils per kilo. It was a randomized crossover double-blind design, as all these trials have been and are. 7-day supplementation period. Again, this was just with 600 milligrams of blackcurrant extract or placebo. And on the 7th day of supplementation, the participants came to the lab. We provided a small breakfast, about 1 gram per kilo of carbohydrate, 2 hours prior to doing 2 hours of exercise at 65% of VO2 max on the cycloergometer. And so these are the results. So we saw a natural increase in fat oxidation during the exercise bout, as we would expect. And what I've actually presented here, just to highlight some of the differences, is total substrate utilization over that 2-hour period. So we can see there was a small change in, or a small increase in the rate or in fat utilization in response to the blackcurrant extract versus the placebo. During that exercise bout, we also took serial blood samples to start to try and understand what's going on in terms of the source of fatty acids, I suppose, that are being utilised to support this increase in fat oxidation. And what we actually observed there was a small increase at the pre-exercise time point in plasma NEFA concentrations. Now that didn't remain different between the two groups during the exercise bout. But at least it gives us some idea potentially that that blackcurrant extract is leading to greater rates of lipolysis and an elevated pre-exercise plasma NEFA availability. So just to, I suppose, bring and pick up a topic that Mark kind of discussed there, is whether we all respond and whether all the participants are going to respond to this in the same way, essentially, to blackcurrant supplementation. I'm going to draw on one of a recent study that he's published, and this is a secondary analysis of all the trials that have kind of been published looking at the rate of fat oxidation and the changes in response to supplementation with blackcurrant extract. So this includes 7 cohort studies, 3 case studies, and it's got a range of participants in there. So there's recreationally active to ultra endurance, and some differences in the dose used as well. And this is the two sort of key figures from the paper, I think. So we've got here on the left-hand side females and the number of, and on the right-hand side the males, and you can see the the relationship that's been plotted here. So this is RER in the placebo group during exercise versus the change in fat oxidation with the blackcurrant extract supplementation. And we can see in both males and females we've got this kind of positive relationship between the two. So what that really is telling us is that those with the highest pre-intervention RERs, and therefore they're probably the highest rates of carbohydrate oxidation under the placebo condition, are most likely to experience increases in the exercise-induced fat oxidation following the blackcurrant supplementation. So those individuals, and this throws up an interesting topic, I suppose, that needs to be explored, is that those individuals potentially following a low carbohydrate, high fat diet, or those individuals that are very endurance trained and have high rates of fat oxidation may not respond in the same way as those individuals who rely a little bit more on carbohydrate as a fuel source. So just worth considering. Okay, so just to build on some of that work that we'd previously done in female participants, and one of the things that I'd always been interested in understanding is muscle substrate utilization, essentially, and for want of a better phrase, I enjoyed taking pieces of muscle out of people's legs and looking at that under a microscope to understand the relative utilization of glycogen and also muscle triglycerides. And with respect to muscle triglyceride utilization, the method that we sort of relied on predominantly was immunofluorescence microscopy. And One of the reasons for that is that it removes the issue of extramyocellular lipid contamination. So when you take a muscle sample from an individual, if they have extramyocellular lipid, that can then contaminate what we're trying to actually measure, which is the intramyocellular lipid and the changes in the intramyocellular lipid. And the other thing using this method is we can look at fibre type specific estimates of intramuscular triglyceride utilisation during exercise. And typically what we get is these nice looking images. One of my previous PhD students claimed that this was disco muscle, which I thought was quite a nice way of putting it. But what these images show here is if we've got this panel here in the type 1 fibre, the sort of pink is the sort of plasma membrane, and then each one of these green spots is, in theory, a triglyceride droplet. And so we can use counting techniques to quantify the number of droplets and the number of spots in those fibres, look at that in a pre-exercise muscle sample compared to a post-exercise muscle sample, and start to understand the rates of utilisation of a triglyceride in a semi-quantitative manner in these different fibre types. And again, this is just a representative information, but typically what we see during endurance exercise is a reduction in intramuscular triglyceride content in type 1 fibres and with very little change really in type 2 fibres. So we then wanted to employ this method to try and understand, well, if we're seeing an increase in rates of whole body fat oxidation with New Zealand blackcurrant extract, then is that having an impact on the utilisation of intramuscular triglycerides? So we then set about doing this study. Again, a 7-day supplementation period. We actually recruited 10 male participants for this one in the first instance. Again, randomised crossover double-blind design. Same doses as previously explored, 600 milligrams of blackcurrant extract or a placebo. And just to note, we took quite a controlled, I suppose, approach with this study to really try and ensure that when we got to this sort of experimental trial and the exercise trial, that participants were starting that trial with the same levels of muscle glycogen and intramuscular triglycerides, because we know that, for example, if you go into a trial with low muscle glycogen, that could then impact your whole body substrate oxidation rates. So 7 days of supplementation, but on the 5th day, they actually came into the lab to undergo a glycogen depletion trial, and then they were refed that evening and the next day with around 6 grams of carbs per kilo body weight. They then came in on the 7th day, had their last dose of blackcurrant extract, a slightly bigger breakfast this time, 2 grams per kilo, and then 2 hours later undertook 2 hours of exercise at 65% of VO2 max on the bike. And one of the things we actually did here, we took muscle biopsies before, actually 30 minutes into the exercise bout, and then at the end of that exercise bout as well. So what do the results show us? Well, first of all, it's worth pointing out again that we saw in this study an increase in whole body rates of fat oxidation with the CurraNZ extract compared to the placebo extract, so that was nice. We also took serial blood samples again, and interestingly this time we didn't actually see a difference in plasma NEFA concentrations between the two conditions. Now, potentially this is just due to the slightly greater insulin response that we're getting with a greater carbohydrate content of the breakfast. We haven't actually measured insulin concentrations in this study, so we'd need to do that to confirm it, but that would be my suspicion. And then we go to the muscle biopsy data, and the title's giving it away, but essentially, yeah, these are some of the images that we've got. We look at quantifying intramuscular triglyceride content pre-exercise after 30 minutes and 120 minutes of exercise, and we can see this sort of stepwise reduction at each of those time points in IMTG content in both in the type 1 fibres, type 2 fibres down here. We don't really see any change in response to exercise, and that's as expected. But when we then determine the net IMTG breakdown, we can see that is actually slightly greater and significantly greater following the blackcurrant extract trial compared to the placebo. So it seems that blackcurrant extract, the increase in whole body rates of fat oxidation, at least partly being driven by greater utilization of intramuscular triglycerides during exercise. We also had a sort of secondary question as part of this study, which was, does this increase in fat oxidation actually have any impact on muscle glycogen stores, and does it actually lead to an enhancement in performance? So one thing I left off the previous slide was this cheeky little time to exhaustion test at 150% of threshold after they'd had their sort of third muscle biopsy. So we wrapped their leg up, got them back on the bike and asked them to do a little bit more work for us, which they weren't too happy about. So some of the data from that, this is the performance data. So it's worth pointing out that they went through a complete familiarization trial in the first instance anyway, to make sure that we could look at some, or try and detect some changes potentially in performance and be happy with those. We can see here that sort of performance was kind of maintained relative to the familiarization trial with blackcurrant extract, but it was slightly reduced with placebo. And when we looked at the sort of statistical analysis there, it came out at about 0.08, so not insignificant, but 9 out of the 10 participants sort of improved or at least sustained performance with New Zealand blackcurrant extract. Was that related to muscle glycogen? Was there any sparing going on? Well, actually, no. This is net muscle glycogen breakdown, and it actually was slightly higher in the blackcurrant trial, which we thought was quite interesting, until we looked at the absolute values. And to our surprise, we'd actually found that muscle glycogen concentrations were significantly greater at baseline following blackcurrant extract supplementation versus the placebo. Now, given the lengths that we've kind of gone to try and standardize muscle glycogen concentrations with this glycogen depletion trial, and then the sort of refeeding process, we were a little bit disappointed, but basically our attempts to normalize this muscle glycogen failed. But it did throw up some interesting information, and ultimately, maybe we can look at this and go, well, the supplementation with the blackcurrant extract is actually enhancing muscle glycogen storage, at least following depletion over this time period. So that was quite an interesting finding, and something we weren't expecting, but given the control that we had in the study and the depletion protocol and the refeed, where we've provided all that food to the participants, we're quite confident this is a solid finding. At the same time that we were doing that study, I actually had 2 master's students working on separate projects, and we were kind of already thinking about, well, is there an effect of New Zealand blackcurrant extract on glycogen resynthesis? And I kind of wish we'd done these studies one after the other now. But one of the questions that we were trying to answer there was, does this short-term blackcurrant extract supplementation enhance acute muscle glycogen resynthesis over a sort of 4-hour period? So a little bit of a complex sort of protocol here, but fairly simple in principle. We recruited 10 trained males, again in this randomized crossover double-blind design, same supplementation protocol as previous. And then on day 6, the participants actually came to the lab, underwent this glycogen depletion protocol, and then they were provided a very low carbohydrate diet. So only over that evening, basically, following the glycogen depletion protocol, 30 grams of carbohydrate, 20 grams of fat and 55 grams of protein. They then came back the next day, and because they're glutton for punishment, we asked them to get on the bike again. They did 45 minutes of exercise at about 50% VO2 max, and then they just performed some intervals just to really drive down muscle glycogen stores. And then immediately after that exercise bout, we took a biopsy. We provided carbohydrate over the next 4 hours at 0.8 grams of carbohydrate per kilo body weight per hour, and then took another biopsy after the first hour of recovery and the 4th hour of recovery to start to look at this this acute resynthesis period. And you might be saying, well, this amount of carbohydrate is probably a little bit suboptimal versus the 1 or 1.2 grams per kilo. That was driven a little bit by what we were actually observing that individuals would do in practice. So you, as we all know, when you're working with athletes, you encourage them to take on carbohydrate after very hard exercise, and they do that to a certain extent, but more than likely, and what we see is they don't hit the kind of recommendation. So we were trying to see what impact blackcurrant supplementation could have when the dose of carbohydrate was suboptimal and the impact on glycogen resynthesis. So results, this is the muscle glycogen data. So we can see very, very low muscle glycogen levels immediately after the second bout of exercise. Slight increase after 1 hour, but then we start to see a bit of a divergence where we're seeing slightly greater concentrations of glycogen in those individuals who had been supplemented with blackcurrant extract versus the placebo condition. And the rate of synthesis over that 4 hours again was slightly increased with blackcurrant extract. It was interesting that, and just going back to what I was saying about the relationship between RER and the change in fat oxidation, what we actually during that 45-minute bout of exercise, we collected expired air. We didn't actually see any differences between the two conditions in terms of rates of fat oxidation under that scenario. But as you can imagine, given the very low levels of muscle glycogen that those individuals were doing that exercise bout under, their RER levels were more than likely, very, very low. And I'd have to go back to the data to show you that. But I'm sure that was the case. So greater rates of glycogen synthesis, again, supporting kind of what we'd seen in the previous study by accident. But interesting, we kind of able to show that here as well. We also took serial blood samples, and just to illustrate here, there wasn't really any difference between the two conditions in glucose concentrations throughout that 4-hour recovery period. And when we express that as the area under the curve, either wasn't different. So we started to think about, well, what's driving this increase in glycogen storage potentially? And we'd actually done another study a few years prior to that, looking at some of the effects of blackcurrant extract supplementation on insulin sensitivity in terms of a health marker and kind of glucose control and regulation. In that study, we actually supplemented overweight and obese individuals because we were more interested in the health kind of side of things at that point, in a randomized crossover double-blind design. So they did 8 days of supplementation with blackcurrant extract or placebo, and on the 7th day they came to the lab, had an oral glucose tolerance test, and then on the 8th day we'd use CGMS to look at the free living glucose regulation. So we're interested in looking at glucose regulation under laboratory controlled conditions with an oral glucose tolerance test. And then equally, we wanted to see, does this hold true when people go back out into the real world, let's say. And so here's the data from the lab. So this is your standard oral glucose tolerance test, 75 grams of glucose, and then serial blood samples over a 2-hour period. And we can see that the blackcurrant extract was able to reduce plasma glucose concentrations and also plasma insulin concentrations, and that held true when we measured the total response there with the glucose and insulin area under the curve. And then also when we calculate insulin sensitivity index, the Matsuda index, then there's a slight increase in the blackcurrant trial. So that was nice and positive. We wanted to then see, does that translate to a free living scenario using continuous glucose monitoring? And quite nicely it does. So this is the trace that we get over that 24-hour period using CGMS. The green is the placebo, the purple is the blackcurrant. And we can see that each meal here, so this is our breakfast, lunch and dinner. And then we looked at the sort of 3-hour postprandial period to understand what was happening to glucose, the increase in glucose and then the subsequent reduction following that meal. And when we looked at the area under the curve, in response to each of those meals, we can see that in response to breakfast and lunch, the blackcurrant extract was able to reduce the glucose area under the curve. We didn't see a difference at dinner. I think that was primarily because there was quite a high fat and protein content of that meal relative to carbohydrate, so we were probably suppressing or masking some of that effect there, at least. But what does this data tell us? Well, quite nicely, it shows that we can improve glucose handling under lab control conditions, but also, I think, importantly, under free living conditions. And that's the big take home for me there. And this greater capacity for glucose clearance may be kind of linked to the improvement in insulin sensitivity. So one of the things that a PhD student at Liverpool John Moores University that I'm still supervising is now looking at is trying to dive into some of these mechanisms, and you'll have to bear with me because this is like very in vitro cell work, and as you can see, what I've presented so far has been very whole body. But essentially what he's doing is using L6 myotubes, and these L6 myotubes that we've started to use have this GLUT4 tag attached to them. And he set up an experiment essentially where we want to understand, first of all, what impact the raw extract has on GLUT4 translocation to the plasma membrane. And so you can expose these L6 myotubes over a time course of 0 to 40 minutes under both control media with insulin which would obviously drive GLUT4 to the cell membrane, the blackcurrant extract alone, or a combination of the two. And generally what we're seeing here, and this is probably the most interesting one to me, is after 10 minutes you're seeing both insulin and blackcurrant increase cell surface GLUT4 concentration. And typically what we see is that both the blackcurrant and the insulin together are kind of having a slightly additive effect compared to either one alone. So there seems to be something in that. Now, as Mark's talked about, and we know from a number of studies that have looked at the metabolism of these anthocyanins, their bioavailability in the blood is very, very low, and they are metabolized extremely quickly once they enter the circulation. So what we should really be doing is exposing the cells in vitro to what the cells in the body are going to be exposed to. And so from the studies we've done, we had a lot of blood left over, as you can imagine. And so we've taken those serum samples and now started to look at whether we can expose the cells to the kind of conditioned serum following a period of supplementation, and understand whether that is also going to drive GLUT4 translocation. And as we can see here, this is the data. So this is just under the control conditions, and then in response to insulin, this is the cell surface GLUT4. And then when we provide either 10% or 20% serum, then we start to see an increase in GLUT4 at the membrane in response to this sort of conditioned human serum. So this is very much like pilot data. I think this was certainly this experiment was produced about 2 weeks ago. So this is very novel, but just to illustrate where we're trying to head with this, to try and understand some of the mechanisms that are driving, the improvements in insulin sensitivity and maybe the increase in capacity to store carbohydrate in muscle as glycogen. Okay, so just to summarize, from my data, we're seeing that the blackcurrant extract can augment IMTG utilization during exercise, may enhance time to exhaustion performance. What it doesn't do is it doesn't seem to spare muscle glycogen, but I think we need to do a little bit more work there. But what it does seem to do, and to our surprise, was to increase muscle glycogen resynthesis or storage, and potentially that might improve the capacity for recovery. Now, anecdotally, blackcurrant extract has had a lot of, I suppose there's a lot of anecdotal reports of improvements in recovery, and we don't really know, recovery is quite a broad term. What do we mean by recovery? And we're still trying to understand that, but I think one of the recovery metrics would be, can we resynthesize muscle glycogen much more quickly, and therefore we can, perform, hopefully again, in a subsequent exercise bout to a better degree. And then finally, what we're trying to understand is, what is driving this greater resynthesis capacity or storage of glycogen? Is it, a greater glucose uptake into muscle? Is it direct effects on glycogen synthase activity, particularly if it's having sort of an insulin mimetic activity? And then maybe there's some effect on microvascular recruitment. So we know that C3G, cyanidin 3-glucoside, can impact like eNOS, which is an important enzyme in microvascular recruitment, for example. And then just to finish off, I just wanted to make the point that this supplement is being used across sport, and the main reason I wanted to bring this back is because when I joined Precision Fuel and Hydration, I actually started to do some work with this guy here, Hayden Hawkes. For for those that don't know, he's a very, very good ultra runner, but he was actually using the supplement at the time. And you know, he's done very well using that supplement. So first at CCC at UTMB in 2017 and 2024, Black Canyons 100K 2023, and then I watched him essentially try and chase down second place at Western States 100 last year, running a 5:28 mile. Now I can't say that that's due to currants. That might be the carbohydrate that we're selling him, but an unbelievable athlete who's using that supplement, and I just wanted to, it's kind of gone full circle for me there, so that's good. Awesome, so I'd just like to acknowledge, so at the moment we've got, so Harvey did the glycogen resynthesis study. This is Lawrence, who's currently doing a PhD at Liverpool John Moores, which I'm supporting. This is Jen Barrett, who's helped out a lot with these studies, and then Dan Owens is now leading that PhD. With some of that in vitro work, and Jules, who helped me, as well as Mark, for his introductions for me to blackcurrant. But yeah, thank you very much.